I've never heard this before. I think that's a misunderstanding of how the protocol works. It's definitely not mining.
Yeah, I think the same too. But like, that's the reason they say the legals are high. So
I think that whoever gave them tax advice didn't understand the protocol. That's honestly my take on that. Yeah, it's definitely not mining. There's no randomness involved with it. There's no lottery. There's no chance to produce it or not produce it. Anybody can come and do the work, and it's fundamentally very different than mining. It's basically what cloud providers are doing. It should be taxed the same as what any SaaS service is doing, because you're running software as a service and you're selling it back to the network. So yeah,
that's a huge relief,
Yeah, no, it's definitely not mining. That's crazy.
And the second one, what is the communication layer between the snark workers and the validators that buy the proof? Like, how do they communicate and how do we assure liveness there?
So there's two mempools in the network. There's one mempool for transactions and there's one mempool for snark work. So the snark workers are submitting snark work they've completed back to the network's mempool layer, the gossip layer. They're gossiped around the network. And the mempool, similar to like transactions, you're keeping only the higher fee transactions. You're keeping only the lower fee snark works. And so it's basically a very simple operation. When you receive a snark work via gossip, you're like, oh, for this specific work in the pool, because you know exactly what work exists in the pool that needs to be completed. Do I have a lower fee already? And then you throw it out, or just lower and then I take it. Does that answer your question? There's no direct connection to the validator, just the entire gossip network that is providing all the snark work.
So the selling process of snarks is also a transaction in the network in a way?
It's not a transaction, but it's gossiped in the same way transactions are.
And then they get the money to their Mina account, right? That exists in the state.
Yes.
So is it included in a future block, the payment?
It's included immediately. It's just not proven until a future block. So at the point in time where a block producer buys that snark work, they're immediately having to, and it's proven as part of our snark proofs, they immediately have to transfer the relevant Mina to that snark worker.
And do they connect to the layer through an RPC of validators, or are they like light nodes, snark workers?
Well, snark workers are actually not nodes. There are snark coordinators, which are nodes that coordinate work among a whole bunch of workers. They're not light nodes. They are full nodes. They participate in consensus. They are just not producing blocks.
If I was a snark worker on this example, can I start to produce a snark proof for the future blocks? So because I can see all transactions in the first block, and do I have to wait until the third block to come to produce its proof, or can I start producing its proofs for the future?
So you can't start producing the proof for transactions that haven't been added yet. But even though each of these layers here is being worked on in different orders, this is just the ordering sequence. I don't have to wait for that sequence to be achieved by a block producer. As soon as this transaction's in here, I can start working on this. But the problem is I need the lower proofs to know what it looks like to merge that up, okay? So in a sense, as soon as somebody does this proof and this proof on the network, and I see those, I can immediately build this one, okay? So you can eagerly produce snark work well ahead of when it's required by the network. The only thing you can't do is you could try, but it just wouldn't work, is to produce snark work for transactions that haven't been included in the blocks yet. So once the transaction's been included in the block, it's free game to work on any snark work that's in the queue.
Each of the transactions has a specific fee for it. What about the second layer and the third layer of that tree, right? Is there a higher incentive to do those, or is it?
You're not paid with the transaction fee of the... So the snark work fee that you're charging is not paid for from the transaction you're proving it for. It's paid for with future transactions because block producers need snark work to make space. The snark work has to be included in blocks. Block producers have to do that to make money. If they don't include snark work in blocks, they will not make money. And so it's the block producer's job to find a way to pay for that work from all the transaction fees in that block. You basically, the way it literally works is like, in a block, you take your Coinbase and all the transaction fees you get, that is the total sum you made for that block. And you have to use that money to pay out snark workers. But also, you can include less transactions if you don't buy enough snark work. And block producers actually do this, they run this algorithm where they're like, oh, if I buy this work, is it going to let me include enough fees that I'm making profit? And there becomes this sort of like profit push and pull thing that's going on inside of block producers, where they're like, actually, I'm going to stop right here and wait for a cheaper work, because this work they're trying to charge is too expensive, and I'm not going to actually make my money back from future fees I'm going to include in this block. That's part of the marketplace.
But thus far, because the Snark place has been just zero fee,
Yeah.
There hasn't been such situation.
Well, there has been. During times of high throughput on the network, like after epochs happen where people do all these staking reward payouts, actually you do see Snark fees come up. Snark workers do end up charging non-zero Snark fees, and they do include in blocks. And sometimes you'll even see, because people take advantage of this when there's a lot of congestion on the network, this actually should not be as much of an issue in Berkeley, because we've tested this in Berkeley. But one of the things that would happen is when the network would get too congested with all these transactions, the gossip network would not work super well. And so it became a little inconsistent, the gossip around this information. So some Snark workers would come online and charge really high fees. Like they charge tens, if not hundreds of Mina for that. And a block producer would be forced to include it, because otherwise they wouldn't get their Coinbase at all.
And block producers usually have an algorithm that just catches the lowest fee for the snarks.
Because there's that mempool model, every node is only listening to and keeping the lowest fees on the network. They're throwing out any high fee ones as long as they've seen it. The thing is, when the gossip becomes inconsistent, which once again is much better on the new network, then they can take advantage of that, because you haven't actually seen all the work that was out there, because maybe you missed it due to gossip inconsistencies. So. So I'm going to take a little pause on all the technical details to talk about what are the properties that we've gotten so far by building the blockchain in this way, right? Like, why are we doing all this zero knowledge proof stuff? Why are we doing it all in parallel? I'm going to talk about that really quick. So I'm going to compare Ethereum and Mina, but really this is a placeholder for any blockchain. I'm picking on Ethereum. Most of these things are true for Bitcoin as well, but I'm picking on it because it's the most similar, it has an account-based model. And most other chains are based on Ethereum, not Bitcoin. So there's sort of like two interesting axes that we want to think about things from, is like the cost of verifying information and the cost of storing information. So I'm going to talk about it in terms of O-score. I think everybody's familiar with big O notation. Okay. So basically, for anybody who's on the video, big O notation is just a way to describe the way that operations scale. So if I say O of n, that basically means like it's scaling linearly. The more stuff there is, the longer it takes, or the more data you have to store. If something scales O of 1, it means that regardless of how much more stuff there is, it's just, it's constant time. It's constant storage space, okay? So when we're looking at Ethereum, if we want to verify all the blocks, we have to look at all n blocks. And within all those blocks, there's all the transactions, and we have to look at all n transactions. We basically have to go through all n blocks, all n transactions, and reapply them from the beginning to figure out what the current state is. This is so prohibitively expensive on Ethereum. It would take many, many weeks of a very powerful, expensive computer to do this, that people just have learned to trust the chain. They just trust those they contact. They just trust that the network has operated correctly in the past. In theory, if the network had a very short period of time where there was a cartel that was agreeing to do something bad, you wouldn't know in the future unless you redo this operation. You're putting a lot of trust into the network itself. In addition to that, because you need to have all this information around, you have to constantly store all n blocks and all n transactions, and you have to store all n accounts, because the accounts are the state that you're applying everything to, okay? Comparing the Mina, and Mina, because we have this recursive zero-knowledge proof that's already proven all the blocks, we only need to do it in O1 to check the blocks, because we're just checking the proof of the blocks, which also means you're checking the transactions, so that's O1. And because you don't have to keep them around, the network doesn't need to store them, so it's O1 in terms of storage of blocks and transactions as well. The network doesn't have to actually grow in storage space requirements as the network is continuing to operate. And so it scales into the future basically forever. That never changes. This constant amount of storage requirements and constant amount of verification time is the same. The only factor in which Mina scales O of n is accounts. But what I would say is that this is fine, right? Because, the high throughput here is blocks and transactions. This is every interaction anybody ever does with a chain. Number of accounts is just how many people are operating with the chain, how many apps are on the chain. And so this is sort of the least important of all these scaling factors in a sense. So Mina doesn't erase this. You do need all the accounts. You need that whole ledger, store the nodes, but you only need the most recent ledger. You don't have to store, even really the original ledger. Everybody knows the Genesis ledger, but it's not actually important from the perspective of joining the chain. What these properties here get you is this amazing light client story where you can come and you can join the network from your mobile phone, from a web browser. You could join it from a satellite in space, as we were talking about recently. And so the idea is like, because it becomes really cheap to join the network trustlessly, it completely removes this aspect of Ethereum where you have to only run full nodes and otherwise you have to trust, right? If you're in the browser, you can't do any of this stuff. If you're in a mobile phone, you can't do any of this stuff. You can't even download this data, let alone actually run the computation. It would take like a year on a mobile phone probably. That's just a number I pulled out of my ass, but like I don't think it's entirely unrealistic. It would take a very long time to do that, and nobody would ever do that. They don't want to spend that amount of time checking the network. Every time the network moves forward, you have to redo parts of that computation. And so the big advantage of Mina with the recursive zero-knowledge proofs is not just scalability of the chain itself, it's also the ability to just be able to join the chain from any device anywhere very quickly. This operation to download an individual block and then check the proof is very, very short. It's like tens of milliseconds of time to actually do the verification.
And that's for the light nodes, correct?
It's for full nodes too.
Full nodes too?
Yeah. Even full nodes. So this one just means it's constant, okay? The amount of data you have to download from a full node is a bit more than the amount of data you have to download from a light node, okay? Because you have to download all the accounts, and you actually have to download K blocks. That's like 290. It's not quite K, at least K. We'll just say K for now. It's, if you're looking at forks, sometimes you download more. But you'll download K blocks, but the thing is that this K is not moving. This is a constant number. It's not scaling as you have more blocks. The network only has to keep the K most recent blocks. For a full node, you're downloading K, but K is still constant. It's still O of 1, okay?
So in the 22 kilobytes, the famous, do we include hold accounts or it's just the constant size? And if you include all the accounts, doesn't the account count increase like dramatically when there are zkApps, because we also should store the states of zkApps?
So, okay, let me talk about the 22 kilobyte thing real quick. So the 22 kilobyte number is kind of interesting. It's not the data you need to sync a full node to the chain. This is what 22 kilobytes is. 22 kilobytes is downloading a block header. It's downloading the proof for a block that you check against the block header. The block header is basically the public input to that. That's what the proof is certifying. And it's also downloading one account from the ledger and doing a Merkle proof for it. Okay, so in other words, 22 kilobytes is the amount of data you need to check one account, okay? It's actually less than 22 kilobytes if you're just trying to check the chain, okay? So this is the way I like to think about it. It's about, I think, don't quote me on this, but it's about 11 kilobytes to get the block and the proof for the block. And then any account that you want to look up, like per account, you're doing like another 10 kilobytes. I think maybe it's 9 or something. I forget the exact numbers. It's around there. So the answer is 22 changes based on how many accounts you're verifying from that state. The real thing is that it takes 11 kilobytes of data and 10 milliseconds, not tens of milliseconds of time to basically check the block. And then you can request individual accounts from the ledger that block's verifying. And each of those accounts you're downloading is like some few more kilobytes of data.
In the Mina full nodes, whole accounts are always available, right?
Yeah.
In all accounts.
Yes. So in a Mina full node, to sync to the chain, you have to download all the accounts in the ledger. I think the ledger is like hundreds of megs right now. So it's not terribly large. With zkApps, it does get a little more, right? As you have more zkApps. That's part of the reason why on-chain storage is limited, is to help keep that number small. We'll still bump up on-chain storage in the future, most likely, almost certainly. But that is sort of the trade-off there that you're making, is the number of accounts that you have in the ledger. You do have to have all those in the full node. But as I'm kind of arguing here, that's the least important scaling factor. That's like based only on how many people are using it, how many apps exist in the chain. You're always keeping constant for actually syncing to the chain. And then you can just look up the individual accounts that you need. And so even in like a very long time, let's say, I wish I had the numbers for this, but let's say the account was millions and millions and millions of ledger. But like the ledger was millions and millions and millions of accounts instead of like the hundreds of thousands of accounts we have right now. This is only going to be a handful of gigabytes. It's like 2, 3, 5 gigabytes of data, right?
Then is there a reason specific for to choose 8 state fields, or it's just number you like?
I don't know. I didn't choose 8. We were going to increase it, but then there were memory issues, so we didn't. So we can increase it in the future when we fix the memory issues. There are some memory issues right now with the node. That's why we had the soft limit. Somebody was asking about that earlier. Of like 24 zkApps per block is also related to this memory issue. It's not an unfixable memory issue. It's a memory issue only in technical implementation because you actually don't need a lot of the information in RAM. This is like information that's accessed very infrequently. So we're just naively storing a lot of information in RAM right now. All you need to do is write it to disk. And once again, that amount of data is not in. That amount of data is O of 1. So it's a constant size amount of data. It's just once we threw zkApps in, because zkApps are a lot larger, that constant size grew to like, tens and tens of gigabytes of data you have to store in RAM. You can store those tens and tens of gigabytes on disk instead. But you throw it out over time. It like, as the network progresses, you throw out the old data. And you really don't need all this data to join the network. You only need the account information and the K blocks to join the network. This is information you accumulate as you're verifying new blocks coming in and doing start work and things like that. So it's like ephemeral data unrelated to the ledger.
When we say the verification cost of transactions, you said it's O of 1, but I need to download n accounts to verify the transaction history, or can I like download some partial amount and verify that's
when you check the block proof, you've verified all transactions of all accounts.
But we don't need the account.
Even if the account was verified because it was a private input to the Stark. The public statement the Stark is making is just the Merkle root. So the Merkle root is being publicly attested to, but all of those accounts that were fed into, like the accounts are basically the states that were created from the transitions from Genesis, right? And so all of that information is actually folded into the private inputs of all the Stark proofs, so you don't need to serve it with the proof. The only information you're actually checking with the proof is that Merkle root, and that's attesting to all the accounts. So I don't need to download all in accounts to verify them. That proof verified all in accounts for me. And once I look up an account that's related to that Merkle ledger and I do that Merkle proof, that's this piece of information here, that like some like 10 or less kilobytes of data I had to download to get the account plus the Merkle proof for the account. Then I know that's connected back to the Merkle root, and I know that that was part of the statement that the Stark was building.
But for Snark proofs, the verification time is constant, but the proof size is not, so it depends on the accounts. So
no, Kimchi is constant size proof.
And also constant size verification.
Yes.
Only generation time that increases number of accounts.
No.
What else increases?
When you're doing an individual proof, you're only doing 2 Merkle lookups in the source ledger and 2 Merkle lookups in the target ledger. With zkApps, we break that up into a whole bunch of account updates, where each account update can only look at 1 Merkle root in the source ledger and 1 Merkle root in the target ledger. That's like the transition of that account, right? But we break those up into individual chunks and then prove them separately.
Going back to this, so would the chain work without any problems without archive nodes? And if so, how archive nodes kind of fit in it? It is just for historical lookup, or is there any other advantage of having archive node?
Yeah, archive nodes are only for historical lookup. The chain does not need archive nodes. Archive nodes are not required for consensus. They're essentially a sidecar to the network. So, people are incentivized to run archive nodes because they want to run explorers, they want to see the history, and that history can be proven back to the most recent block as well. Proving historical information back to the most recent block costs O of n in terms of transactions that you've done on that account since then. However, that's like only in the case where you're doing a historical proof of information of something that happened way in the past. Usually the way you're building a zkApp is you actually have this statement you're building up every single time, so you only need to look at the most recent statement. So it's generally you design around this. So some applications, some zkApps may rely on archive node, but you can design your zkApps to not rely on archive node, which is what you should be trying to do. But the network itself, the consensus layer, absolutely does not need any archive nodes to run. You could run the entirety of Mina with 0 archive nodes. The network still works fine.
I see. And then for the case of RPC, you still, in the full node, have access to last 250, K nodes,
yeah.
K blocks. So in theory, you still have access to an archive of the latest archive.
So one question I got during the break was, I should have explained this better. Why are we doing all this work in parallel? Like, why do you not just prove all the transactions of a block immediately in one big zero knowledge proof? And the answer of that is basically scalability of transaction throughput and block proving time, right? The point is that we want to divorce block proving time from the throughput of the network such that we can scale the throughput of the network heavily regardless of, without affecting block proving time, right? In other blockchains, like Ethereum, they actually have this additional problem where their throughput is limited by how fast a ZKVM can run. In other words, the amount of transactions they can fit into a block will always be limited by how fast they want that block to be produced, because they have to run through every transaction and execute every single EVM operation on all of the smart contracts that are interacting in there. Mina's block time is only limited by the time it takes to apply transactions, and none of those transactions include any kind of execution. So we're basically able to do this really cheap operation where we're just updating some things in the ledger and checking a couple of pieces of information, and that's the amount of time it takes to produce a block. And in fact, we actually do a lot of that verification ahead of time, like checking the proof and things when we put it in the mempool, and we're just doing some really simple state checks when we apply transactions to blocks inside of Mina. And so we have this thing where we get to divorce execution of contracts from block time, and then we also get to do in parallel all the proving of those transactions without affecting block time as well. So that's why we spend so much time on parallelization. Okay, I'm going to talk a little bit now about consensus, because I talked about this great property, but we should talk about how our consensus mechanism actually enables this, because this whole problem is like, well, okay, I can check a block and of one, but how do I know it's the block? How do I know it's the one related to the network? And how are we actually proving inside of the block header that this block is the right block that I should be looking at? So really high level, I'm just going to compare two different kinds of consensus mechanisms people are familiar with. You have Nakamoto consensus, which is typically based on proof of work. And you have BFT proof of stake consensus, which is basically Byzantine fault tolerance. That's where you have proof of stake, but you basically elect validators at any point in time in the network, and those validators produce blocks, okay? So I don't think I have to draw much for this, so I'll just talk. In proof of work, Nakamoto consensus, basically the way that works is you take the longest chain. You just take the whole thing and you turn it down to this longest chain rule. Proof of work is taking computational power, in a sense. I guess I can draw this. Proof of work is taking computational power and it's divvying up your right to win blocks in the network. Wow, what a bad pie chart. Based on how much computational power that you have, right? And so the idea is that you want to distribute access to produce blocks. And in proof of work, you're doing it on computation. That's all these slices of the pie, is how much computation you're putting into the proof of work. And so the idea is that as long as more than 50%, 51% at least, is actually acting honestly on the network, then you can trust the chain. And what that means is that with 51% of the chain, of the computing power going to one version of the chain, you can just look at the longest chain, right? So that's the longest chain rule, is basically what Nakamoto consensus relies on. Proof of stake is similar, except with proof of stake, what we're doing is we're trying to divvy up your right to win blocks based on the portion of the stake you control on the network. So instead of looking at your computational power, it's looking at the stake distribution. And there are a couple different ways of solving this. One is to keep Nakamoto consensus, which is what Ouroboros does. And I'll revisit that in a second, but I'll talk about BFT for a second, okay? BFT is the popular solution for this. And the way the BFT works is that you look at all these different slices of the pie of people who are staking in BFT, and the network works together to elect the validator. So at any point in time, they say, okay, we're going to run an election. All right, you won. So now for the next period of time, the next few hours or however long they choose, they usually choose a shorter period of time, you're going to produce all the blocks, okay? Now, this puts risk on the network, because if this person controlling this portion of the stake on the network doesn't actually act honestly, or they just fail to produce blocks, the whole network is paused. The whole network is stopped. And so what BFT does is they do stake slashing, where they're like, okay, well, you need to put some of your stake up, and if you don't act well, then we're going to get rid of your stake here. Okay? That's basically how BFT works. Now, there's an issue with BFT when it comes to trying to do this recursive zero-knowledge proof, okay? One issue is performance and efficiency. Doing this like whole validator election cycle basically involves getting signatures from most of the nodes in the network and then proving all those signatures. That can be really expensive to do in a Snark. It is doable, but that has been a limitation. But as Snarks get faster, you can actually do that reasonably. Like especially with folding, you can fold all the signatures together into one witness, and then you can just say, hey, here's all the signatures, here's the election cycle. The problem with BFT, when you're adapting it into zero-knowledge proofs, is that this stake slashing situation, imagine the situation in which somebody did not produce blocks. How do you prove somebody didn't produce blocks? You're proving a negative. You can't prove a negative, right? It's like an impossible thing. Maybe you could have a whole bunch of people sign signatures together to say like, this person didn't participate, but then you're just putting trust in this like signature coalition, which could just be a cartel of people that decided, hey, I don't like this validator, I want to get rid of it too. And so that's really not good. And this is a problem with a lot of BFT mechanisms. They're all basically relying on this historical trust. But if you're trying to use a zero-knowledge proof to sync to the chain and say you have these properties, then you're really even going further down that road. Because anybody could go produce a zero-knowledge proof that's sort of continuing the chain, ignoring blocks, right? I can just censor blocks arbitrarily for my zero-knowledge proof. Does that make sense? What we want to have instead is we want to have something more like Nakamoto consensus, because what Nakamoto consensus gives us is we have to prove the validity of a block, but then we get this simple rule to select between a series of blocks about which one's the most valid block, right? What was that? Yeah, the longest one. Well, we'll get to that. It's more complicated in Ouroboros than the longest one. But the idea is the same, right? Naively, if instead we can take a proof of stake consensus, but then we could have some kind of longest chain-like rule, then what we do is we don't have to worry about the situation where we're proving a negative. Nobody has to get their stakes slashed because lack of participation just means you're not in the chain. It means you're just missing out on money. It means you're just not participating in the honest portion of the network, which only has to be a certain percent of the network. So the way that Ouroboros works is instead of actually doing these validator cycles, which puts all the risk on the network into one person at any point in time, and then having to worry about a way to slash the stake, right, because that person didn't behave correctly, we're instead basically letting everybody, if Ouroboros is an election, if BFT is an election, Ouroboros is a lottery, okay? In the same way that proof of work is like taking up that pie chart and distributing work among it, and that's basically the lottery, right? This is how proof of work works, is like a lottery. We're doing the same thing with proof of stake. We're taking up all the different portions of stake, and that's your chance to win every single block. But we divide blocks up into finite series of times called slots, and every single time there's a slot, every single person on the network participating in block production is going to basically roll a die locally, in a sense. And if their die came up with a good enough number based on what their stake was, then they can produce that block. And so what happens here is that, you get all these different forks where different people won different blocks. And if you notice, unlike BFT, we have a situation that's more similar to proof of work, where you can have multiple blocks being produced by different people at the same time because they both won the lottery. And in fact, in Ouroboros, it's very possible, more so than with proof of work, that you have like 4 or 5 blocks that all won the same slot, or perhaps slots where nobody won blocks, right? And so what this creates, in a sense, is a very forky network, right? We're going to keep on branching because different people have seen the blocks at different points in time, okay? This is the reason why probability, you were asking before about probability in Ouroboros, this is why probabilistic finality in Ouroboros tends to be longer than in like regular Nakamoto consensus.